Hello and welcome to Calculus 2, Chapter 10, chapter on sequences and series. We are going to dive into what we call discrete mathematics, where we move away from our continuous functions f of x, from our continuous input x, into what we call a discrete input, which is just counting numbers 1, 2, 3, 4, 5, and so on. So the counting set n, we put two vertical lines, and then n is the set that contains natural counting numbers starting at 1. We do not start counting with 0. Even though we actually, in mathematics that we are going to do, we can start with 0 if we want to. And we can start anywhere. But the important thing is that your input numbers for your discrete functions that we are going to use will all be given as 1, 2, 3, 4, 5. So those of you who are in computer science, that's your little case, right? Lowercase I. When you say I++, I++ means, right, just the next number. Increase the value by 1, right? So this is it, and the variable replacing your x is now called an n, right? So that's going to be our n variable. And we get to define sequence. Sequence is an ordered list of numbers. That's it. The word, what's the key word in the whole thing? Ordered. Very good. Ordered. Right. So sequence is the ordered list of numbers. Its notation will be a sub n. And we are going to have terms. We'll start with a0 because computer science. So we are mimicking the array, right? One-dimensional array for you guys. And it can be finite with, 7 terms, let's say, or infinite with infinitely many terms, just like our counting set that goes from 1 to infinity, but it goes as integers, 1, 2, 3, 4, 5, 6, 7, and so on. All right, so now, this is our definition, and this is where the cloud goes. So this is one of those things that you absolutely must know. Can the question on the test be define the sequence? Yes. And what do you write? What's in a cloud? Nice. Anyway, what are the examples? Well, I can say an is equal to 3n minus 1. And we can start counting at n equals 1, 2, 3, 4, ... So if I choose to start counting at 1, I can write out the sequence of numbers. You plug in 1 for the first value. So that's going to be 3 times 1 is 3 minus 1 is 2. Plug in now 2. 3 times 2 is 6 minus 1 is 5. And you quickly pick up the pattern that you are supposed to just add 3, and you will go to infinity. That's an example. Another example, say bn, could be 2 divided by n squared minus 1. Now we have an issue here. Can I start counting at 1? No, because you make computer explode, right? So we have to start counting at 2 in this case, because, as I said, 1 would make denominator 0. So now what do I have? I have 2 squared is 4, minus 1 is 3, so 2/3 is the first number. Then when I plug in 3, that's 3 squared is 9, minus 1 is 8, so 1/4 is the next term. Then when I plug in 4, 16, 1, 15, 2 over 15. Then when I plug in 5, 25, 24, 1 over 12. Dot, 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 going on. You're allowed to literally make anything you want. Cn, let's say n to the n. It's okay. We'll start counting at 1. And we'll have 1 to the 1 is 1. 2 squared is 4. 3 cubed is 27. And 4 to the 4. Very good. And then we'll have much larger numbers following. I hope you understand that this an takes the role of the function f of x, and your variable n takes the role of x. So you can make that connection with your mathematics that you had so far. You at least know the way to compute these sequences, and we see that they're ordered because this term here was produced with n equal 1. This term was produced with the next term, n equals to 2. This one was produced with n equals to 3, n equals to 4, and so on. So that's where the word ordered kicks in, where every term is computed in order where the n's rise from either 0 to infinity or 1 or 2, depending on the structure of your problem. You are not allowed to ever skip a value. Never. Never ever you will be skipping one of these. That's why the word ordered is there. All right, so I don't know if you would agree, but it's pretty easy when you have the formula to come up with a sequence. Good one. Now, we get the sequence, and you are supposed to come up with the formula. Those are the fun times. So let's see. Given, and now we're going to have some sequence. Find an. So you're looking for an. So now let's come up with some sequence over here. So let's go with this is an easy one. So 1, 1/2, 1/3, 1/4, 1/5, dot, dot, dot. 1 over n. Okay. So immediately by looking at this, you see that it's all numerators are 1. Denominators go 1, 2, 3, 4, 5. That's n. And you state that n started counting at 1, right? Can we come up with a different value? Yeah. Or you can say an is 1 over n plus 1, and you start counting at 0, right? It's okay. If your first value is 0, 0 plus 1 is 1, 1 over 1 is 1. Awesome. So that one works as well. So some of these you can start counting at 0, some of them can count at 1. Some you must start at 1, right? Some you had to, we had the one where we had to start counting at 2, because 1 over there would not work. So that was that. All right, let's take a look at some spicier cases where you so given blah, find formula an. Okay, so let's make it more interesting. So 1, 1/2, 1/4, 1/8, 1/16, ... Excellent. 1/2 to the n, and you start counting where? 0. Because 2 to the 0 is 1, 1 divided by 1 is 1. And then 2 to the 1 is 2, you have your 1/2. Then 2 to the 2 is, right, 4. 2 cubed is 8, 2 to the 4 is 16, and going on. Awesome. Ready? Let's see. Depends on how much I want to break my head to come up with these examples. So I'm going to start with with the simple examples, and then maybe think harder. We'll start with 1/2 this time. My head is literally it's lazy to compute right now. All right, so here we go. So the first one will be 1/2. Then we're going to have 1/3. Is that right? Yes. No. I don't want a 1/3. I want. I don't know. It's just there's no reason for me to think. I can just hibernate. I'm just gonna place some secret numbers over here, the Illuminati code, okay? And then just make stuff up for you to enjoy. Don't be looking at the way the pencil moves. $1,307,000. Okay, good. You gotta love it when they make no sense. You guys have it already?
Yes.
Oh, I gotta make this much spicier. What do we got?
12 over n squared plus 1.
Oh, nice. Where do we start counting?
1.
At 1. What happened? Oh, it's now competitive over here. Okay. This is the last one. Now, I'm not going to give you any of those that you possibly can't know yet. So, you should be able to figure this one out. Key on should. Bingo. Yes, so when I start listing these as you guys. All right, so -2, +2, 2 over 7, 2 over 25, 2 over 79. Oh, this one is not easy. Unless you already have the answer. Good? Let's talk. We see that there are denominators everywhere. Since there are denominators everywhere, I'm going to put divided by 1 to fill those denominators. Immediately what I see is that everywhere except on the first one I have a 2 on top, which means that this negative belongs in denominator. So I am going to now rewrite this as 2 divided by negative 1, 2 divided by 1, 2 divided by 7, 2 divided by 25, 2 divided by 79. Which one?
2 and 3 to the n minus 2.
Got it. 2 over 3 to the n minus 2. Boss. And then you ask yourselves, what are these numbers close to? This one is clearly 5 square.
I didn't have any chips. I hope you like oatmeal raisin.
Well, thank you.
He's finally arrived.
Yeah, I know. Woohoo! Well, thank you, Mel. Nice. We have, what was I talking about? So when you look at the list over here, right? We have just 1 squared is 1 and 5 squared is 25, right? So we clearly see it's not nothing squared. So this is a good time for you to go through the lists of those counting numbers, even numbers, odd numbers, and so on. So I'm going to write those. So this is and you only have 5 of those, right? You already know most of them. We'll add factorials and some others, but here are the ones that you should know. N is equal to 1, 2, 3, 4, 5, 6, going on. 2n is the way to write even numbers, and that's going to be 2, 4, 6, 8, 10, going on. The next one is 2n minus 1, which would give you 1, 3, 5, 7, 9, and so on. Now we're getting into n squared, which is 1, 4, 9, 16, 25, dot, dot, dot. And here is the n cubed. N cubed is 1, and then 2 cubed is 8, and 3 cubed is 27, and 4 cubed is 64, and then 125. And then you have your 2 to the n, which is 1, when you plug in, well, let's start them all at 1. So 2, 4, 8, 16, 32, and 3 to the n. And this is the one that you probably didn't know. 3, 9, 27, 3, 9, 27, 81, right? And then 3 to the 5, so 243, going on. So these are the lists. This is your even numbers. These are your odd numbers, and you will see these way too many times in life, right? Now, if you carefully look at this one, if you are to add 2 to each one of these numbers, what do you get? You get 1, 3, 9, 27, 81, and that is your 3 to the n sequence. So you added 2 to get to the 3 to the n. Take away 2 to get the numbers that you have, and then 2 over, and that's how we get this thing. Now, obviously, these numbers here will be useful to you only for the problems where you have the sequence, and then you want to compress that into a formula, and you hope that something like this. Now, these are not, very frequent problems. Those of you going to differential equations using power series, you will have to use some of this stuff, but not much. Next step for us is to learn the new creature, factorials. Notation, n factorial. This is not n, it is just n factorial, right? It's a notation. We put this, just mathematical notation. So nothing to be excited. Yeah, nothing to be excited about. Definition for a factorial is that n factorial is equal to 1 times 2 times 3 times ... times n minus 1 times n. You are multiplying integers up to the value of the factorial. Now, you will be sick of factorials, especially if you're taking discrete math. So, make sure you know this stuff. Examples. 6 factorial is 1 times 2 times 3 times 4 times 5 times 6, altogether 720. You can multiply them in any order, I don't care. 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360 times 2, 720, if you multiply them backwards. Right? If you multiply forwards, 2 times 3 is 6 times 4, 24. 24 times 5 is whatever you get times, it's 120. 120 times 6 is 720. Now, this is interesting. I'm going to write it in blue. 6 factorial can be written as 6 times 5 factorial. Would this make sense? Sure. 5 factorial contains the numbers 1 through 5. And then times 6 creates a 6 factorial. It could also be written as 6 times 5 times 4 factorial. Exactly. Because the 4 factorial is going to contain. So you can peel off as many numbers as you need. And you probably saw something like this in statistics if you did those coefficients for binomial coefficients and you did your counting and stuff like that with factorials. So the permutations and variations, the n choose x and so on. I mean x choose n, whatever. All right, so these are our factorials. And it will help, in some cases if you know, at least first 6 factorial numbers. Now, I will write here in red, 0 factorial is 1. 1 factorial is also 1. 2 factorial is 1 times 2, 2. 3 factorial is 6. 4 factorial is 24 because you multiply the last one with the 4. 5 factorial is 120. 6 factorial is 720. And I promise you that you will not be going past 6 factorial to do this. Now your calculator runs out of memory in calculating 70 factorial. 70 factorial, it breaks your calculator memory on TI-8384. Newer calculators can power through it. For some research I did, I took 121 factorial, and that when you use standard margins in Microsoft Word with the standard spacing on a font 12, took 3 pages of digits on 121 factorial. The next factorial I actually worked out, which I had to use the code for, was 1,331. You recognize those numbers from the Pascal's triangle, hopefully. So there's 1 and then 1, 1, and then 1, 2, 1, and then 1,331. 1,331 factorial after coding returned 27 pages of digits of Microsoft Word. So yeah, these factorials rise insanely quickly. They are faster than your exponentials, and they are still slower than n to the n. So they will fit in between world of exponentials and the world of n to the n. N to the n, the boss function, right? It's the fastest growing function that we can use in its. I mean, there is faster stuff, but it's the fastest function. Okay, cool. So now that we understand these sequences to some degree, we are able to generate sequence given the formula, or given the sequence, figure out the formula, take a look at these factorial values, and knowing these, so we're going to add this one right there. I told you 5 that you might have to memorize. So 1, 2, 3. Yeah, okay, I was good. Plus the factorial, right? So, I mean, you probably already know the square numbers and so on. I wasn't counting that you had to memorize even and odd numbers, right? Or accounting numbers. I thought you guys knew that from the first grade on. Okay, no one is complaining. That's good. So the rest of the numbers you might have to brush up on. Okay. The next idea is going to be graphing. And for graphing over here, we are going to take a look at the world that we now live in, which is the world of, let's say, an is equal to 1 over n, versus the world of f of x, 1 over x. So this is the two worlds that we are going to compare. And I'm going to carefully, now we know that we have to start counting in this case at 1. So what I'm going to do is I'm going to say 1, 2, 3, 4, and then 1 and 2. That's my n axis, where I have counting numbers. Again, nothing in between the numbers exists. There is only integers, 1 and then 2 and then 3, and nothing in between. So now when I use number 1 and plug in a formula up there, 1 over 1 is 1. So I get 1, 1. And then when I go and plug in 2, I get 1/2, and then 1/3, and then 1/4. And then if I draw one over x, I get to draw the lines. So now we see the difference. Now here's your 1, 1, here's your 2, 1, here's your third, and so on, right? They still exist, but so does everything else in between, including the negative branch, right? So The AN world, the discrete world, only has these discrete dots. And that's like impulses, right, for the computer. You can think also the heartbeat, right? It strikes, then again, right? So in these even intervals, there is some kind of value. Now I'm also going to graph another one. Let's say Bn, call it 2n minus 3. Let's graph that. Now, when you are graphing these sequences, there's going to be my Bn over here and the n as an input. When you are graphing sequences, you do not have to waste your paper to go to the left of, right? Because you start counting at 0, which is on the y-axis, or you start counting at 1 or 2, right? So you don't have to waste your paper, right, to draw like here, right? This whole branch to the left. Okay, so if we start counting and let's say 1, 2, 3, 4, 5, plug in 1, it's going to be negative 1. And then plug in 2. 2 times 2 is 4, minus 3 is 1. Plug in 3, that's 6 minus 3 is 3. 4, 8 minus 3 is 5. 4, 5. Is this good? Right? It's good. Now, what do we see? When we look at these two graphs, hopefully I can place them. Here I go. We can see both of them. On the top graph, we see this trend of these points. You're not supposed to connect them, but I'm connecting them to show the trend. It looks like that they're going to fall and they're going to stay at the level y0, right? Now, that kind of a concept where the sequence tends to a finite value, we are going to say converges to that value. So, because these values, the AN values from our list, from a sequence, because they tend to go smaller and smaller and smaller, but never reaching or crossing the x-axis or the n-axis, which is the AN equals 0 level, or y equals 0 level, we will say that something like this converges to 0. Now, the bottom one, as you can see, it grows without a bound. We will just call that divergent. So now we are talking over here convergent versus divergent. Converges meaning goes to a finite value. I don't care what that value is. Could be a negative value, positive value, could be 7, right? All of those are convergent. Divergent go either to positive infinity, negative infinity, or they oscillate. And now it's time for us to take a look at one very important, written in red, alternating sequence. Alternating sequence is given by negative 1 to the n, or negative 1 to the n plus 1, or any of those combinations, right? So we can focus on, I'll put the cloud. We are going to have alternating series as a section. So alternating sequence is important. All right? So alternating sequence is just this negative 1 to the n. Now, what is negative 1 to the n equal to? Well, if you start counting at 1, it's going to be negative 1, positive 1, negative 1, positive 1, right? And it's going to go to infinity. Is it? They're going to go forever, right, as infinity in n, which is doing the counting, but this sequence will never go above 1 or below negative 1. What is this good for? Well, it's good for alternating sequences. Maybe you are going to say, given blah, find an. And now the blah over here is going to be the same blah you had before. Let's say you have 3, and then 3 halves, negative 3 halves. And then we're going to have positive 1. And then we're going to have negative 3 quarters. And then 3 fifths. And then negative 2. So the first thing that you see looking at this is plus, minus, plus, minus, plus, minus, right? So you know that whatever you come up for the sequence will be multiplied by that version, some version of negative 1 to the n. It's either negative 1 to the n or negative 1 to the n plus 1, depending on where you have to start counting for your, because it's not just you have to figure out the counting for the actual fractions, but you also have to figure out counting to start with a positive or negative, right? Because if I'm starting my counting at 0, right, then that's going to be a positive 1 to start here. So you have to be careful with these things. All right, so what's my sequence? Is it obvious or hard?
It's 3 and the alternating sequence
Over n. Excellent. So if you fill in your denominators, and then you realize that all of your numerators should be some multiple of, oh, this last term is not good. Last term was supposed to be negative half, right? Yeah, negative term was supposed to be negative half. All right, good. So now, if I multiply this one over here by 3 to fix it, I will get 3 over 3 on that one. So now, if you take a look at your denominators, it's just 1, 2, 3, 4, 5, right? 6. Because this one would be times 3, it will be 3 over 6 to get the numerators the same. So we know it's 3 over n, just to take care of the fractions. And then I need negative 1. Oh, where did I start counting? I started counting at n equals 1, right? To fit the fractions. So now I just need to figure out, do I need n or n plus 1? N plus 1? Excellent, yes. N plus 1, because if I just leave it as n, first n is 1, negative 1 to the 1 would be negative 1, so the first term would be negative. So we must use n plus 1. You can also use n minus 1, whatever. It just can't be n. Awesome. So you can play these games and figure things out, but make sure. Oh, here is another. Let's use purple. More alt sequences, obviously, dare I say obviously, cosine n pi. Isn't that the alternating sequence? Cosine of 0 is?
One.
And cosine of pi? Negative 1. And cosine of 2 pi? 1. And 3 pi? Negative 1. 4 pi? 5 pi, 6 pi, 7 pi, 8 pi, 9, right? So this is equal to, when n starts at 0, this is 1, negative 1, 1, negative 1. So you can also get your alternating term in. So this is if you really want to be sophisticated, right? And someone says, what do you know? I can make alternation with the cosine. And then sit down and explain for another 2 hours the rest of the stuff that goes with it. I want to challenge you to give me the formula for alternation given sign of stuff. I'm in the meeting with my destiny. N pi over 2. Amazing. Excellent. And it's going to start with 1. You have to start counting with 1. Because if n is equal to 0, sine of 0 is 0, so it doesn't fit the pattern, right? You have to start counting at 1. And it starts 1, negative 1, 1, negative 1, going on forever. Cool. You're doing great. Yes?
1, 0.
0 is next.
0.
Big 1, 0, 0.
Why?
Because sine pi equal to 0. 1n equal to 2. That's sine pi. Sine pi equal to 0.
So, what? When I plug in 1, I get pi over 2.
Yeah, when you plug in 2, you get sine pi.
Oh. Yes. We are only allowed to have odd numbers here. Yes. This n needs to be odd numbers.
2n plus 1.
2n plus 1, yes. If this one doesn't want to erase, it looks like set in stone over there. Never forget that. 2n plus 1, there we go. So now it's, when I plug in 1, that's 2 plus 1, 2n minus 1. 2n minus 1. Much better. You wouldn't expect for sine to be worse than cosine. There you go. It's possible. Cool. So now we understand that, okay, so we have this, and now in red again, nah, it's too early. Later. All right, still in red, but now this is the big guns. Test for convergence of sequences. Guys, this is the first out of 11 right now. First out of 11. Ready?
Yeah.
Sequence AN converges to L if the limit n goes to infinity of an is L. Otherwise, it diverges. Done deal. Cloud. In good old times, I would tell you keep the track of all of these on the cover of your notebook, but then I will provide that sheet of paper which you can further copy, make, smaller copies and laminate, so you can put that little hole, so you can put it on a necklace or something. Make sure you laminate, because if the paper gets wet when you shower, right, it completely, this is a thing you will be going out with and going to the, right?
You don't just tattoo it on your arm.
Tattoo on the arm. I mean, that's.
What if I do that?
Number.
Yeah. Can I just have that at the exam then?
Yeah, because I can't really peel it off your arm.
Well, you wouldn't make me cover it up or something?
I can't, because I don't dictate your dress style. So there's literally nothing I can do.
I think we found a loophole in the system.
See, everyone goes to the closest thing place.
Like right down the road is tattoo parlor.
There, let's look at it. The what?
We all get tattoo sleeves of this.
Tattoo sleeves is just these statements, yes.
One statement over and over again.
Yeah, can you imagine over there? You're working, it's like, how much? $100. What if I bring you another 29 people? For the same one. All right. So sequence would converge. Guys, you see what it's up. You just do the limit, right? You are taking the limit. This is your 2.5. If it gets nasty, 4.7 for L'Hopital's rule. And now, when I show, this is old edition textbook, but the new ones will have the pretty much same examples. Limits of sequences, find limits for sequences to determine if the limit does not exist. Does it converge or diverge? Falls under basic skills. Well, let's do some basic skills. Yes. L'Hopital's rule 4.7 from Calc 1, which is when you have 0 over 0 or infinity over infinity or 0 times infinity or infinity minus infinity or 0 raised to 0 or 1 raised to 0 or 1 raised to infinity. Just those cases. There are a couple of full 2-hour lectures on it. You can't miss it. Okay, let's take a look at some of these wonderful examples. And they will we should have you there all the time. And as you can see, your ability to take these limits, right, will impact your ability to solve these problems. So let's take a look at some of these. Well, I'm going to start with the simple examples that we already had as graphs, right? So if my an is given as 1 over n, then the limit n goes to infinity of 1 over n is equal to 0, right? So we will say converges to 0 and problem is done. That's it. That's all, right? Another one we had was bn was equal to, I believe, 3n minus 2 or 2n minus 3, doesn't really matter. If you say limit n goes to infinity of 3n minus 2, the answer would be infinity, and we'll just claim divergence because it doesn't go into a number, which is what we have up there in the definition. So if the limit goes to a number, it converges to that number. If the limit goes to any of the infinities or it oscillates, it's divergent. Now let's take a look at some of these wonderful exercises provided in here. They would like to know let's say Cn is equal to n to the 12 divided by 3n to the 12 plus 4. Yes. So we will take the limit. N goes to infinity. N to the 12 divided by 3n to the 12 plus 4. And you said 1/3. Answer is correct. Why?
Divided by the highest power.
Excellent. From Calculus 1, section 2.5, when you have two polynomials, you will divide every term by the highest degree present, in this case n to the 12. When you divide everywhere by n to the 12, divide by n to the 12, divide by n to the 12, everything reduces down to 1 divided by 3 plus 0. When you divide 4 by infinity, you get 0, because 4 is a finite number, and you are dividing finite number infinitely many times. Guys, anytime you divide, you make the answer smaller, right? So when you divide something by infinity, that answer that's getting smaller goes to nothing because you're dividing it infinitely many times. So this 4 over n to the 12th term will go to 0, and you just get 1/3. So converges to 1/3. By the way, this is your, over here, guys, this stuff is your 2-point answer. You can't end your problem and circle 1/3. Right? You have to say converges to 1/3. That's the answer to the problem, not that, right? Let's see what else they have. Let's say, dn is equal to tangent inverse of n. Limit as n goes to infinity of inverse tangent of n. Oh, remember how I drew this function the first day? So if you flip your notes to the day 1, it had to be there somewhere in the review on the Calc 1 prep or Calc 2 prep, whatever I called it. I am all ears.
What was it?
Inverse tangent of x graph. Nope, 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 nope. Yes? Not 1, not infinity. Nope.
0?
Converges to? Nope. You already tried that.
I thought it was 1.
You think if you say it enough times that I will change that my answer to the answer.
Pi over 2.
Pi over 2. Converges to pi over 2. That's the answer. I will draw tangent inverse of x, and then you just imagine it with all of the dots. So these are your two horizontal asymptotes, and the tangent will snake through sideways like that. Pi over 2 and negative pi over 2. Oh, the inverse tangent will be back. So it's good to know it. Ooh. Shiny. Let's go back to AN. One plus 4 over n raised to the 3n.
Just at that time.
Clearly, since we are looking for convergence, we want to know the limit as n goes to infinity of 1 plus 4 over n raised to the 3n. This is one of those limits that you should just look at it, write a solution without any calculation, and be done. Should, I said. And also will. Not necessarily now. Does this look like anything? We will have to do L'Hopital, yeah. But does anyone recognize the form of what the answer should be? We just have extra garbage around, but the the form of it.
Should that be 1?
Mm-mm.
Red.
Nope. All right, so I'm just going to write it down because by now, if anyone knew it, you would say it instantly without thinking about methods to solve it. This is e to the 12. The form is e, and you just have 4 times 3 is 12, which creates a nifty limit formula for you to remember so you are not doing what I'm about to do. The nifty formula is limit n goes to infinity of 1 plus a over n raised to the bn is e to the ab. So that's the a times b. You pick up a from that spot and b from the other spot and you just multiply them together. And that's how I got e to the 12 without doing any work. Now, what does it take to solve the limit if you don't know this rule? By the way, you only see that the definition of e is when a and b are 1, right? So 1 plus 1 over n raised to the n is just e, right? E to the first power, which is e. And that's the definition for e. Calculus definition for e is limit n goes to infinity, 1 plus 1 over n, everything raised to the n. That's the definition for number e. But if you have these a and b involved, then you have e to the ab as the exponent. Okay, cool. Now, let's take a look at refresher 4.7 L'Hopital's rule, 1 to infinity, right? That's what we have to use. And if you don't remember any of these things, there is study plan, video lectures, textbook pages, my office hours, phone a friend. It's like a lot of different options you have. Let's go. We start by setting the unknown limit to y, and we're going to ln both sides, so I'm leaving some space. 1 plus 4 over n raised to the 3 to the n. The only way for me to kill that 3n exponent is to use ln so I can pull it down. That's that p rule that we used in the past. So now I have ln y is equal to, put the limit in front, and now I have 3n ln of 1 plus 4 over n. Now, when you check your, right, to plug in infinity, the first one over here, 3n, will give you infinity, right? And the second one will give you ln of 1, which is 0. So you get infinity times 0. When you have infinity times 0, we are using the trick, algebraic trick, f equals 1 over f, and that will change it into, in this case, 0 over 0. So ln y is equal to the limit n goes to infinity. Ln of 1 plus 4 over n stays in the numerator, and then 1 over 3n is shipped into the denominator. That 1 over, you know what, I can kick this 3 all the way in front of the limit, so I don't have to drag. You know, I'm going to just use the blue color and kick 3 outside, so I don't have to drag this 3 with me. It's just convenience and laziness. All right. So what do I have now? When I plug in n equals infinity, I get ln of 1, which is 0. And 1 over infinity is also 0. So now I have 0 over 0, which means I can use L'Hopital. By the way, this is Bernoulli's rule. If you didn't take my Calc 1, I emphasize it. L'Hopital was the first one to publish, so everyone thought it was his rule. And then by the end, they figured it out. Everyone was dead. So now we have our ln y is equal to 3 times the limit n goes to infinity. And now I am taking 2 independent derivatives. The denominator is easy, negative 1 over n squared. And now in the numerator, I have ln. So that means I have my 1 plus 4 over n, and then times the derivative, which is negative 4 over n squared. So now I'm going to multiply by negative n squared to kill the double fraction. And I have the ln y is equal to 3 limit n goes to infinity. On the denominator, everything cancels. On the numerator, negative and negative will cancel. I have 4 divided by 1 plus 4 over n. When I take the limit, this one will go to 0 because 4 divided by infinity is 0, and all I get is 4 over 1, which is equal to 4. Oh, sorry, 3 times 4, which is equal to 12. There we go. Right, so the limit over here is equal to 4, and then you have times 3. So now we have ln y is equal to 12. If you e both sides to kill off your ln, you come up with y equals e to the 12. But then if you remember all the way up there, you defined your y to be the limit that you are looking for, right? So if y is the limit you're looking for and y is e to the 12, then the limit you're looking for is 12. E to the 12, I mean. And that's the procedure to come up with the answer. So now, one more step left. Converges to e to the 12. That's 2 points right there. After like half a page of calculations. If you don't know the limit. So for these e limits, you either know the purple formula or you don't. If you don't know it, then luckily you know L'Hopital's rule, right, to come up with the same answer at the end. Do these problems pop up? What do you think? Of course. How many of them do you see in the homework alone, right there? Number 19, right? This one, 20, can be converted into it. square root of it right here, the one we just did, right? To some extent, this works out. How about 26?
Yeah.
How?
What's this? Oh, it has a minus.
Yeah, it has a minus.
That screwed everything up.
Yes?
It's plus a negative 4. Plus a negative 4.
Yes! Nice! The answer is e to the negative 4. You just take this negative and glue it to the 4. It stays a plus there. And you just have negative 4 for a, b is 1, and there you go. So e to the negative. So you should be able to do all of these problems just by looking at them, right? Right. Good. Now, do we have some more interesting? Yes, of course. How about the 24 and the 25? So let's see at least one of those. The other one you can enjoy for homework. So let's see if your, let's say, Bn is equal to ln of 1 over n divided by n. Your job is to take the limit of n goes to infinity of ln 1 over n divided by n. This should be way easier than the previous one. And we're also going to do some mathematical flexing on it, because we can. Oh, actually we can't on this one. We'll make it worse. What's the answer?
0.
Would you bet your life on it? All right, let's go and take a look. I think well, the answer is correct, but let's take a look. So when I plug in infinity, I get ln of 0, which is negative infinity, and then infinity. So I have infinity over infinity, which means that I can do the L'Hopital rule, which is we put this L apostrophe H over equal sign, and then we have limit n goes to infinity, and now we take our derivatives. The denominator derivative of n is just 1, and in the numerator the derivative is, for ln, it's 1 over n times the derivative of this one, which is 1 over n squared. Negative 1 over n squared. So now this is limit n goes to infinity. We need to clean up the algebra. So 1n will cancel, and all we have is negative 1 over n. The limit is 0, and we just say converges to 0. Awesome. There are a lot more problems, and there are a lot more trig problems, and it will really benefit, guys, for you to now remember. I understand we have another 30 seconds, but this needs to be written down. The growth rate of functions, because if you have the limit, just like this problem here, if you have the limit that goes to infinity, where you have two functions that are from different family of functions. This belongs to log functions. This belongs to polynomials. Okay? It is very easy to deal with limits when they belong to different families. So now we have to start off. We start off with the sluggish family, and that's going to be your ln of n. Then a little bit faster than that is your root of n. Then faster than that is n to some power p. Then faster than that is going to be your exponential raised right to the n. Faster than that, we said it's going to be your factorial. And then faster than that is going to be the boss n to the n. Now, what I'm going to write here is mathematically not correct notation, but it has to be written. All right? In some countries, I probably would drag on a square and shot, but luckily no one did that yet. Limit as n goes to infinity of slow divided by fast is equal to 0. Put that in quotation marks because this is mathematical sacrilege. Now you understand what this means. If you take any function to the left, right, put it on top, and any function on the right, put it on the bottom, the limit will always be 0. And limit of fast over slow is going to be infinity. Again, quotation marks. Now, this works only for n goes to infinity. It doesn't work if n goes to 3 or 0. Only works for infinities. So now, if you take a look at the previous problem, I have a family of limit of ln, which is the sluggish one, divided by a polynomial n. So n is a faster growing function. On the long run going to infinity, n is going to win out over log big time. If you graph the log, and you graph n, which is x, you see that it wins big time over the log. And you know that in between, you get to squeeze in the square root, right? Then the x squared and so on. Then you have the exponential function, do like that and so on. So you see them all, right, stack up. And every time you go to the next tier, this pushes more to the left and it rises faster as it goes to infinity. So it wins quicker and crushes the other one. So the limits are always either 0 or infinity when you have these functions. Now, the scariest examples are the ones when you have infinity, minus infinity with the functions that are matched, and then you have to figure out those and right all of these kind of things with exponential for L'Hopital and so on. I think I saw one of those somewhere. Yeah. I'll just give you this because I know class is over and you want to go home and do nothing. So have fun. AN is equal to, and we can start with this on Wednesday. N squared plus 1 minus n outside of the square root. So this is infinity minus infinity. We did not have any infinity minus infinity today. We had the exponents, we had the basic divisions and so on. So this would be something interesting to consider. Bye. I know, right?